Here is the filament in a tungsten lamp. As the filament is heated, it emits energy in the form of light. Although the light appears white to our eyes, when we pass the light through a prism, it is separated into a continuous spectrum of colors. This continuous spectrum shows that a tungsten lamp emits photons of all energies. This is a gas discharge tube containing hydrogen. The light emitted by this tube is due to hydrogen atoms. Let's look at the spectrum of this light source. This time we see a line spectrum. Each line corresponds to just one possible energy change in a hydrogen atom. We see that very few energy changes occur in hydrogen atoms in contrast to the tungsten filament. Accurate frequency measurements tell us the energy changes and lead us to the hydrogen atom energy level diagram. But how can we explain the fact that the energy of a hydrogen atom has only these certain values? We begin with a simple picture of the hydrogen atom. At any given instant, the electron is separated from the proton by some distance, r. The electron and the nucleus have opposite electric charges, so they attract each other. This attraction gives the atom a certain amount of potential energy. The amount depends on the distance, r. The electron is in motion, and so the atom also has kinetic energy. The sum of these two kinds of energy is the total electronic energy of the atom. This sum expresses the laws of motion that apply to macroscopic particles. To fit the observed behavior of microscopic particles, like electrons and protons, the laws must be modified somewhat. As modified, these laws are called quantum mechanics. The mathematics of quantum mechanics are quite complex, but we don't need to consider the details of the calculations. Our interest is in the results that quantum mechanics gives. This high-speed computer simplifies the task of carrying out the calculations. The equation is punched onto cards and fed into the computer together with instructions on how to solve it. The computer then rapidly solves a problem that is tedious if done by hand. When the calculations are completed, the machine types out the energy values. Let's compare these calculated energies with the experimentally determined energies of the hydrogen atom. Agreement is excellent. Thus we see that quantum mechanics provides an explanation for the specific energies observed for the hydrogen atom. Because quantum mechanics also confirms all other properties of the hydrogen atom that can be measured, we believe the results quantum mechanics gives for those properties that are more difficult to measure. One such property is the location of the electron relative to the nucleus. What can we learn from quantum mechanics about this? To answer this question, we will consider the 1s state, the lowest and most stable energy state of the hydrogen atom. Quantum mechanics gives the results only in terms of probability. A dartboard will help us understand the kind of probability information that we get from quantum mechanics. See where the dart hits. Each throw is completely independent of the others. Observe the pattern of punctures. There are many holes concentrated near the bullseye. Toward the edge of the board, there are fewer punctures. These holes indicate the likelihood that the next throw of the dart will land in a given square centimeter. Where there are many holes, the probability is high. Where there are few holes, the probability is low. These observations allow us to conclude that the probability of the dart landing near the bullseye is much greater than the probability of it landing far away. we shall see that there is a close analogy to the electron distribution in the hydrogen atom. The pattern of holes is centered around the bullseye, just as the electron centers its movement around the nucleus. Compare it to the probability plot for the 1s state of the hydrogen atom, as generated by the computer. What does this plot tell us about the location of the electron? To answer this question, another analogy may be useful: the movements of a hummingbird around his nest. We'll use the hummingbird to represent the electron. His nest represents the nucleus. The nest is located in this small tree in a field of flowers. Let's represent this scene on a chart. Here is his nest in the tree. The hummingbird collects nectar from the flowers here and there around his nest. Let's suppose that we keep a record on this map of the location of each flower the hummingbird visits. Here's one now. We'll mark the location of this flower on the map. Oh, now he's over here. Oops, there he goes. Let's mark it. And now a third. Let's continue plotting these locations. Plotting over a long period of time, a pattern develops. In this pattern, for a given area, the number of pins is much higher near the nest than it is farther away. Again, we have probability information. Thus, we conclude that the probability of the bird landing on a flower near the nest is much greater than the probability of landing on a flower some distance away. We can discuss the average distance of the hummingbird from the nest, but sometimes he will be found closer than this average distance, sometimes farther away. In any event, we see that there are no boundaries to the pattern. Occasionally, the hummingbird lands on a flower a very great distance away. The plot of the hydrogen atom, which the computer drew earlier, has exactly the same meaning. Just as this map tells us the probability of finding the hummingbird a given distance from his nest, so this plot tells us the probability of finding the electron a given distance from the proton. As in our analogs, we see that the probability of finding the electron near the nucleus is much higher than finding it far away. Again, we find that there are no boundaries to this plot, for although the electron is most likely to be found near the nucleus, it occasionally may be found very far away. A limitation of this plot is that it shows probability in only 2 dimensions. We can use animation to add depth to the plot. This probability description of electron location is called the 1s orbital of the hydrogen atom. We note that the orbital has no definite boundaries, although it does have a spherical shape. Thus, the expression 1s is a convenient abbreviation, where the 1 indicates the energy state of the atom, and the S denotes the spherical shape of the orbital. But remember that the orbital represents only the probability of finding the electron at a certain location. If we could observe the electron, at any one instant the electron would be found at some particular location. At another instant, it would be found at some other location. What about the path or trajectory that the electron follows in getting from one location to another? Well, this is a question that quantum mechanics does not answer explicitly. Any trajectory that corresponds to the spatial distribution we see here could be in accord with quantum mechanics. Thus, we can only test trajectory models of the atom by comparing them to the quantum mechanical picture. For example, here is a common model of the electron's trajectory that you have probably seen often. It shows the electron moving around the nucleus in a path similar to that of a planet moving around the sun. We'll call this a satellite model. Let's compare this satellite model to what we have learned from quantum mechanics concerning the hydrogen atom. If the satellite model were correct, the electron would always be at a fixed distance from the nucleus. Then the probability plot would take the form of a circle. The electron would never come very close to the nucleus. But experiments show that the electron does come close to the nucleus, just as calculated with quantum mechanics. Hence, the satellite model is inconsistent with our experimental knowledge of atoms and can be discarded. Although quantum mechanics does not tell us the detailed motion of the electron in the atom, it does tell us the electron position in terms of probability. Far from the nucleus, it is low. Near the nucleus, it's high. We can consider an average radius of the electron position, but there are no boundaries to the atom. The orbital contains only probability information, just like the pattern of punctures in a dartboard, just like the map of the flowers visited by the hummingbird. This plot, determined by quantum mechanics, describes the structure of the hydrogen atom in terms of probability. Quantum mechanics also explains many other concepts of chemistry, such as the energy levels of many electron atoms, the formation of molecules, bond energies, and bond lengths. These successes prove the usefulness of the quantum mechanical view of the atom.